Hello, my name is Edgar Gephardt, and this is Lab 3, the magnetic field of a bar magnet. So, the purpose of this lab was to determine the behavior of a magnetometer at different positions relative to a bar magnet, to create a computational model of the magnetic field produced by a dipole both on and off axis, and to visualize the magnetic field that was produced by the bar magnet in a computational form. So, the basic models we used here is the Biot-Savart law, which we're given a little simplification of for the code, and the distance dependence equations for the magnetic field, which say that the magnetic field of bar is equal to the constant k times r to the n, and that the natural log of the magnetic field in the x direction was equal to the natural log of that k value plus n times the natural log of a variable r. So, preview our results, the n variable is found to be negative 3.1828 meters, and the magnetic dipole of the whole magnet was found to be 6.425 joules per Tesla. So, the experimental procedure, the meter stick was set to be orthogonal with the magnetic north along the east-west axis, and readings were taken from the bar magnet using the magnetometer on the Firefox app on a cell phone. So the location of the magnetometer in the phone was estimated by moving it perpendicularly along meter sticks, and the phone was moved to different distances to obtain different Bx values at 2070, 120, 170, and 220, with those distances being recorded. So it was measured both on axis and at a 45-degree angle, as seen in the graphic, and these components were recorded and linearized on an Excel spreadsheet. So while seeing this, we can make some assumptions. These are what I saw. As the magnetometer moves closer to the magnet, the x component of the magnetic field increases, and when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. The other assumptions in the lab were not true. So here's our on-axis data. Essentially, we just recorded it. It seemed there was a relationship as the phone got closer, the magnetic field increased greatly, needing less distance to go up more, and it linearized our data and put it into this graph. And the off-axis data was very similar, except for that this case, when we measured, we had a measured equal distance in both dimensions, both x and y, and also the by had to be corrected by subtracting the by of the Earth from it. So the by of the Earth had to be measured, and then had to be subtracted from the by to get the corrected by, and then the spreadsheet calculated the total magnetic field off-axis for us. So, for our calculations, first we use the distance dependence equation from the linearization of the on-axis data, so the slope would have been equal to n, which in this case is negative 3.1828, and then we use the Biot-Savart law for the magnetic moment, and so we know that the magnetic field in the x direction is negative 13.5651, because that was the intercept on our line, and we can just assume that r is equal to 1, because why not? And then the natural log of this k is equal to that bx, and so that k is equal to e to the negative 13.5651, making k equal to 1.285 e to the negative 6. And then we plug into the equality equation that kr to the n equals mu naught over 4 pi times 2 times the dipole moment over r cubed, and plug in our values. We get that mu, which is the magnetic dipole moment, is equal to 6.425 joules per Tesla. So here in the coding, essentially we just create a function that establishes what a dipole is by using the Biot-Savart law that we were given in the lab, and then we set a distance, which in this case is arbitrarily set to 0.25, and a scale. We create observation locations both on axis and off axis, so on all x, y, and z axes, and then we create arrows that point in those directions, and we ultimately create something that will express the net magnetic field at 45 degrees off the axis. So here's the computational readout, and you can see that the calculated magnetic field at 45 degrees at distance d of about 0.25 is 1.8533 e to the negative 5, 5.55989 e to the negative 5, 0. So what if I hadn't oriented my experiment to compensate for magnetic north, and instead laid out my meter stick at some intermediate angle with respect to Earth's magnetic field? So taking magnetic north into account sets the initial x component magnetic field to 0 teslas at the start of our experiment, so only the magnetic field of the magnet will be considered in our experiment. Otherwise, Earth's magnetic field would interfere, and the value in the x direction would not begin at 0 Tesla, meaning you'd have to calculate and subtract the bx of the Earth in those calculations. If I were to stick two identical magnets together end to end and run the experiment again, the value of the magnetic field would definitely be greater than the magnetic field from the experiment, but it is not necessarily double just because that's not necessarily true. So to conclude, some possible sources of error were magnetometer location miscalculated in the phone, and just technological and human errors when measuring. But our computation model is able to use the calculated values using the Biot-Savart law and the distance dependence laws to accurately create a magnetic field at a 45-degree angle off axis of the magnet. So, yeah, thank you for listening.